and I think it's going to be very interesting for all of us. So, in case you have, we will interrupt you.
Oh, you must. Yeah, I think that's really essential because
if you are not clear enough.
Generally not.
Thank you.
Enrique has given me a clear description of how I should present this talk, beginning from one end to the other. So, unfortunately, I've ignored all of that advice, as usual, because in the interest of time. And so I've tried to cover the news regarding this interpretation of the dark matter, which has gained a lot of popularity since we published these first simulations of how structure should form in the context of a coherent light bosonic description of the dark matter. So this is sort of taking the opposite, the opposite approach than WIMPs, where you're typically thinking of very heavy fermions. These are very light bosons, and they can be very cold in the condensate state, so when they share the same wave function. And for these very light bosons, the number density is so high that they are effectively inborn in the ground state and can therefore be expected to be very cold. So on large scales, there's no problem regarding them fitting with the results that we see in terms of the dark matter. On large scales, the properties of clustering of this is just the same as cold dark matter, because the dark matter is not relativistic, and we've demonstrated that here. Is there perhaps a point? Maybe this one. Oh yes, here we go. So this was our first paper, and I mentioned that 2 or 3 years ago when I was doing the talk one time. So you see that there's a lot of momentum built up behind this. And especially with the difficulties now facing CDM in terms of this new edges detection, and also the increasing tension astronomically with low mass galaxies, and of course the fact that there has been no detection of any candidate dark matter particles in the lab, as some of you, I guess, are heavily involved with, right? So then this becomes more relevant. Although on its own merits, it stands, I think, despite what you may feel about WIMPs. So, now what we found in these simulations is that, that there's a lot of small-scale nonlinear structure. And this structure was recognized by the first papers on this work, including Renan Bakana, and they realized that simulations are required to understand this, but these simulations are very difficult, much more demanding than n-body work, because you have to follow the self-interaction under gravity of the wave function. So actually, conceptually, it's not particularly difficult, but it is a numerical challenge. And so I'm sort of fortunate to be involved with the calculations that made the first simulations of this, which have since been confirmed by other later work, including Ostreicher and Witten, who have now, they have come on board and clarified some of the open theoretical questions, and very much proponents of this axion approach. In particular because of the connection to string theory. String theory, as you know, was no shortage of light axions. In fact, this is a landmark paper someone may be familiar with, basically making the point that generic to string theory is the formation of, one can expect, light axion modes that are discrete in mass and span many decades in mass, and can be light through this non-turbative mechanism by which axions can gain mass. they're not subject to the usual problems that light particles have in the context of field theory. So this is motivation then, theoretically, for considering light axions, axions being spin zero, being bosons. So this is a simulation of how a structure will form if it is light and bosonic. And the only free parameter in all of this is in addition to the usual cosmological parameters and the perturbation spectrum, which we take as given, in addition to that, there's just the mass of the boson. I may interchange between boson and axion, but it's the same thing. So you basically have to follow this interacting system here between the perturbations in the dark matter, in the distribution of the matter, so just Poisson's equation since we're dealing with non-relativistic dark matter, and this Schrödinger Poisson equation where the potential is just this one here. So that equation you need to just keep solving iteratively, numerically, and you can then you can see how structure develops. And on large scales, as I say, there's not much difference between standard CDM distribution of matter, but on small scales you can notice there's a lack of tiny structures, and that's because of the de Broglie scale that you associate with the momentum in this context. So that by tuning that mass, you can eliminate small scale structure. That's an advantage because, as we know, there is a shortage of small galaxies, at least in terms of the visible material. Now, here's again a comparison between this wave dark matter and the early times, and you'll see that all these small scale structures are missing, and we have here very smooth filaments. And this is going to be important in interpreting this new edges experiment. When objects collide, they will excite interference. So the whole pattern is an interference pattern, and develops smoothly from very smooth beginnings. That's the point, that there's a lack of small-scale structure here because the power spectrum is suppressed below, it's basically an inherent gene scale in the dark matter. The dark matter has a gene scale. So this relates to the fact that you have the uncertainty principle preventing the accumulation of structure below the de Broglie wavelength. So you see that once structure starts to form, filaments form first, and there's a period when there are only these sharp filaments, and then relatively large mass galaxies compared with CDM begin to form. And they of course merge together, and you get in the end a familiar mass function, but with an absence of very small structures. There are some small ones, and we'll see that something more about that. Well, here are the mass profiles of those halos from the simulations, and you see that they follow a family of curves that are on average NFW-like in the outskirts. This famous Navarro-Frank-White parameterization of cold dark matter actually seems to hold here, but there's all this granular de Broglie structure, so only azimuthally on average do we find these smooth curves. And in the center is the ground state of the condensate. So the equilibrium structure of these collapsed structures has this pressure-supported small-scale structure that includes not only this de Broglie granular structure, which is fluctuating slowly, but a stable soliton in the middle. And you can see that we can fit these inner cores with these curves, which are just a numerical solution of that Schrödinger Poisson equation when you remove the time dependence. They form solitons. So it's not surprising in a sense. But what the simulations reveal is just how rich is this structure, and that the size of this soliton and its mass scale clearly with the mass of the whole halo that's collapsed. So keep that in mind, that the lowest mass, this is the lowest mass object in this simulation here, so do something like this, has the widest soliton, because the momentum associated with this object is low, so the de Broglie wavelength is long, and that sets the scale. And you can see that for the more massive, for a galaxy like our own, we should expect 100 parsec. That's still quite large, larger than central black hole. And we think we have evidence for that, and I'll show you that soon. So you keep that in mind. The simulations have revealed all this structure and how there's a scaling between this prominent central overdensity. And that's our most vulnerable prediction, because clearly if you don't see that, the whole idea doesn't hang together. You need this ground state, this standing wave must form in this context.
Couldn't you change the mass and make the wavelength smaller? And
you could, yeah, you would, exactly, yeah. If you increased the mass of the axion, you would then, increase the momentum, and therefore the wavelength would be smaller. So that's how we determine the mass, by using that fact. Let me just show you some toy models that we've made. So we've looked carefully at this link between, since I was here last time, between the halo mass and this central prominent core. And we can form these kind of simulations. We can look at tidal effects as well. They are different from standard CDM. So how do we determine, we use the fact that these lowest mass galaxies that look like this. So these are the most common galaxies in the universe. You have to realise that first. Right? It's not spirals. They look like this. The majority of galaxies are this kind of object, and the stars can be resolved in the nearby ones in our own galaxy, and you can see that the motions of those stars typically are independent of radius, and this tells you immediately that two things. One is that the relatively high amplitude of this dispersion velocity compared with the amount of material you see tells you they're dark matter dominated. So once you realise that they're dark matter dominated, and that this radial profile is flat, the motions of the stars are independent of radius, then you can realise, you appreciate that there's a core of dark matter there. And this has been known for a long time. And in the CDM context, they invoke winds and supernovae, and they still have real trouble to explain this, because, of course, the gas is not coupled to the dark matter. At least it shouldn't be, right? So, now this is, just let me mention at this point, because we're going to come back to this, that the velocity profiles of the globular clusters in our galaxy, which are very dense star clusters, drop with radius because there is no dark matter. So you have to keep this in mind, that there's a huge contrast between two very different kinds of object. One is the lowest mass galaxies, and the other are these dense star clusters that clearly don't have an origin like this. And we're going to come to that point and explain it later. So we can look at the star counts and their velocity dispersion, and we can obtain through a simple Jeans analysis the mass of the axion that you would, the boson that you would need, and that's around 10 to the minus 22 electron volts. And this is a number that should be therefore universal. And once you fix that, there's no more free parameters in the simulations, and then all these predictions are very well specified, because you fix that free parameter using the best local data on these dwarf cores, connecting it to the size of the soliton. So we can expect galaxy formation to be delayed in this context, because as I showed you, there's a shortage of small galaxies and they form first. So that lack of them means that, and that seems reasonable now. We know that, from the the good work that's been done here with the CMB, the reionization epoch is later than anticipated. And so, you know, we actually had predictions for that have worked out quite well. But I won't dwell on them today. I'll talk about the new predictions. Another thing to realise is that there should be a limit of around redshift 10 for the formation of the first galaxies. That before that there would only be these smooth filaments that contrast with these CDM type structure where everything by that point is in tiny structure. So because of the small scale power that is suppressed here by the uncertainty principle. So there's a really big contrast between this wave dark matter evolution at early times, and that's why this new data is so important. The first galaxies in the largest volumes that we've managed to simulate don't form till around a redshift of 10. The soliton forms first. That's quite an interesting thing. When we've searched for new, very distant galaxies, this is more the work that I've been doing in the past, has been to use gravitational lenses like this to look for magnified, multiply lensed galaxies in the background. And here's the object that remains that we found a few years ago. There it is. And it's still probably the most distant object known. The fact that we have 3 images of it allows us to obtain a geometric estimate of its distance, in addition to its colours that tell you that it has this hydrogen absorption corresponding to that redshift. So we have models of this thing, and you can anyway that's a different talk. But the point is that we are very confident that there are a few galaxies beyond that redshift, and certainly the density of galaxies has dropped. And as I say, relative to CDM, the ionization of free hydrogen shouldn't begin till later, and so then the optical depth for scattering of the CMB is lower, and that's what's, I think, quite clear now from the Planck. Although the numbers still keep moving around. They seem to be going, and the trend is towards the smaller values, right, all the time. Yeah. The smaller the better in a sense, but although it shouldn't be too small, but formation of galaxies at around redshift 8 makes more sense in this context. And here's the optical. So, granularity is something that I've stressed already. This should affect also the lensing, because locally things will be perturbed, and that's been one of the headaches for a long time. Why is it that quasars, when they're studied, the relative brightnesses vary by tens of % relative to the models? Okay, and if they're seen through this granular structure, that makes sense. So we expect that our critical curves, the Einstein ring, looks something more like this, and that locally there are brightness variations of these quasars. So this is a long-standing problem that is nicely solved with this. We expect 40% fluctuations compared with normal CDM, where they would be much smoother, of only a few %. So again, I'm not going to dwell on that because it's not definitive. But I will say that the soliton aspect is the most crucial. And looking at nearby galaxies, this one here, you can see some evidence for central large velocities of gas in the center, as if they're moving under the influence of a lot of dark matter. This is what's called an analog of the Milky Way, the nearest edge-on Milky Way type galaxy. It's the same rotation speed. And in the center you can notice that there's this dense high velocity gas. Here it is again. So this is a normal rotation curve here, 200 kilometers a second, and then there's this excess. This is a map of how the gas is rotating in the object. So most galaxies tend to show this. Even our own galaxy. It's actually a little harder to study our own galaxy in terms of that gas, but there are stars now detected moving rapidly in the center. This is from some work with the Sloan apogee experiment. So this is and you can see that there's a plus or minus. So in the plane of our galaxy, looking at the central degree, there is evidence that stars are moving rapidly in this kind of way. So there's a plus or minus 100 kilometers a second. But more useful than that is this latest work regarding the motion of stars in the center of what's called the galactic bulge. And we can use this. There are proper motions in angle on the sky now, measured all the way to the center, and also velocities that have been measured accurately, including those stars I showed you. And you can see that there's an excess of matter in the center, and they have modeled it as, well, they're not really been able to explain it, but this remains unexplained. This is a velocity excess that for the bulge of stars in the galaxy you should expect only smoothly varying a maximum of 100 kilometers a second motion for these stars, and instead there's this excess. So we can add the soliton that we predict should be there. The scale of it is about 1 degree on the sky, 100 parsecs, and its mass should be 10 to the 9 solar masses. And we find a very good fit to our the mass that we've been predicting before based on dwarf spheroidal galaxy. So this is this denser soliton. There seems to be good evidence in our galaxy for this, so we're just at the moment writing that up. Now inside that soliton there should be some pulsars, and those will the timing of those pulsars, very accurate clocks, will be affected by the oscillation of this axionic field. The field, as you can imagine, is oscillating, given by its mass. It's on the Compton scale. So there's a Compton scale oscillation of any axion-like field, and that's inherent. And the frequency of that oscillation straightforwardly gives you the axial mass, if you notice this. And the way that affects the timing is through this general relativistic connection between the pressure and the the field is oscillating, and that creates a change in pressure, not in density. And that therefore affects the gravitational timing, and it scales with the density of the dark matter. So in this central region where the density is very high, here, we can expect large changes. So the pulsar timing would be such that the pulsars would arrive more quickly, and then the pulses would be slower and then arrive. So there will be a modulation of this with a time scale